to new file. And let me maximize this screen. Okay, can everybody see my desktop for MultiSimLIVE? Give me a thumbs up if you can see my screen. So here I have a number of different tools, very similar to Tina. These are main headers, and I look for the one that says sources. This one says sources. So when I click on this guy, it opens up a pull-out menu, and I look over here. I have a DC source, I have an AC source. I click on the AC source, I drag, and I want to place it, boom, right there. Once I have it there, I deselect it by clicking somewhere on the screen. Now it no longer has all the things around it. The things around it allow me to flip, allows me to make notations, allows me to rotate. I don't want to do any of those right now. I just want to place it. So now I have it placed. I'm going to hit magnify on this, make it a little bigger so you can see. Cool, nice. All right, everybody see a little better now? I'm going to come over here to passive devices, open up this window, and I've got resistor, I've got capacitor, I've got inductor. So guess what we're doing in the next 2 weeks? This is week 5. Week 6 and week 7 have to do with capacitors and inductors. Okay, so 1 week we're going to be playing with capacitors, another week we're going to be playing with inductors. So this software is perfectly set up to do the remaining labs for us. So I'm going to select resistor. I'm going to click and drag and place one here. I'm going to come over to resistor, click and drag another one and place it over here. Click and drag another resistor and place it over here. Okay, deselect. And I'm going to come over here, schematic connectors, bring a ground, and I'm going to bring ground over to here, let's say. So now do I have components placed on my board in a fashion that is similar to Tina? So far, it's very, very similar to Tina. Okay, just give these some spacing apart. Now, when I go to connect them together, it's a little tricky. Suppose I want to connect a wire from the top of the voltage source to the left side of R1. I come over here, and if I'm patient, give it a moment. In a moment, I will see what appears to be a pencil and a little rectangular block. The hand won't do me any good. I need that little pencil symbol. So double click, no, that won't work. Just have to be, there it is. Had it. Deselect a wire, come over to here, and now that's connected. And the next wire from here, got to deselect. Come on, be nice to me. Hover, there it is, and connect. Deselect, hover, there it is, connect, deselect, hover, there it is, come down here, and connect. Cool. And one more from here, hover, and come down and over and connect. Cool. Okay, so we have 3 resistors, we have a voltage source, and we have them in this sequence. We want to change our values, so I double click this guy, and way over on the right hand side, you see I've got 1 kilo. I'm going to select 1 kilo and change this to 2 and enter a K and hit enter. I now deselect, now this is R1 is now a 2 kilo ohm resistor. R2, I'm going to double click this guy, come over here to the far right hand side, select the default value, type in 3K and deselect. Select the third one, select the default value, type 5 kilo and deselect. Confirm that I have 2 kilo, 5 kilo, 2 kilo, 3 kilo, and 5 kilo. as we did in the original schematic I presented to you. Double click the voltage source, and it starts off as peak voltage. I want to make this 10 volt peak, and it is now 10 volts. And how do I know it's 10 volt peak? Because here I have a choice. I can say peak or RMS. If I do this as RMS, type 10 and enter, now the screen will actually show me 10V RMS. Now my voltages here can be measured with a digital multimeter. I don't want to do that. I want my voltages in this particular case not to be RMS. I want them to be peak. Still want it to be 10. Deselect. And so without any nomenclature after the 10, it's defaulted as a 10 volt peak. So right now this schematic is identical in value of voltages and resistors to the circuit I showed you earlier. I'm going to move this guy over here. I'm going to move this guy up here. And I'm going to hit grapher, waiting for data. Here's the schematic. I want to split. When I hit split, I can see an O-scope display, and I can see my schematic side by side. So that is accomplished by hitting this little split thing here. Over here, I've got a run simulation triangle, and I've got a stop simulation triangle. If I hit run simulation, and then over here, normally, let's see what we've got here. Probe. Oh, silly me. I need a probe. I got ahead of myself. So I'm going to come over here, grab a probe, and I'm going to set a probe on this point. Oops, come here. Probe number 1 goes to this corner right there. I'm going to grab a probe number 2 and put this guy right here. And I'm going to grab a probe number 3 and put it right there. Okay. So now I've got 3 probes on my schematic, and look at where I've placed them. This one's a little bit high. I need to place it correctly. I want to place it on the wire. There we go. So I happen to have a green probe, number 1, placed at the corner between my voltage source and my first resistor. I've got a second probe in this lighter blue color placed between R1 and R2. I've got a third probe placed between R2 and R3. Now these are single point probes. Where's the black lead connected to, my friends? Ground. Okay, all I need to show is the red lead, the hot lead of my probe connected where I want. So what am I measuring here? Probe number 1 will measure the total voltage from here all the way to ground. Probe number 2 will measure the probe from the second and third resistor to ground. Probe number 3 will only measure the third resistor to ground. So let's see if these numbers will appear on our O-scope display in a moment. I will come up and hit play. Nice waveform, whole lot of cycles, and too many cycles. So what I'm going to do is I'm going to come to my waveform display, and I'm going to change my time base. See my time per division controller? If I do this and do this, I've got too many cycles. So if I adjust my time per division button here, I can create an easier waveform for us to read. Yes? Nice. Very sweet. Okay, at this point, I'm going to stop the run because my waveform is nicely displayed. And let's go ahead and see if we can read how much voltage we expect at probe number 1. Probe number 1 measures the total voltage across all 3 resistors to ground on this side. Probe number 1 also measures the voltage source from this point to ground on the left side. What is my voltage source? Is my voltage source 10 volt peak? Is the probe green colored? Can you see the green waveform on my display? Can you see what the peak value is if I hover my mouse over this? And notice I can't get my mouse right to the tippy peak, but if I put my mouse right here, can you see 9.9849 volts? Is that pretty close to 10 volt peak? I'll show you something even more interesting. Suppose I now go to the last one, probe number 3. Probe number 3 measures the voltage across the third resistor to ground. What was your calculated voltage for VR3 to ground? Wasn't that 5 volts? Did we calculate 5 volts peak on your VIR chart? And if I hover right here, is my hovering on the screen pretty close to 4.95, 4.99, pretty close to 5 volt peak, yes? Okay. What do you think will be the voltage from probe number 2 to ground? On this side, I've got the sum total of V voltage across R2 and the voltage across R3. What did we calculate the voltage across R2 to be? Wasn't that 3 volts? And wasn't this 5 volts? So from the light blue probe, probe number 2, going to ground in this direction, should we expect 8 volts? And that's the light blue probe at probe number 2. And if I hover here, am I pretty close to 8 volts? It shows me 7.9879. That's pretty close to 8 volts. Isn't that amazing? Now, I'll show you something else even more amazing. On the left side of my screen, there's an area called cursors. Right now there's none. If I go ahead and pull this guy down and I select cursors on the y-axis, it automatically gives me 2 cursors. If I move cursor number 1, grab cursor number 1 and pull it all the way up to the top of this, is there a voltage reading for cursor number 1 down here in the lower left-hand corner of my O-scope screen? Is cursor number 1 shown as a bright green? And is cursor number 1 shown as 10 volts? Because I've laid this cursor line right at the tippy top of my green waveform. We start off with a 10 volt source, 10 volt peak source, and we confirm 10. I'm going to place cursor number 2. I'm going to grab cursor number 2, and cursor number 2 I'm going to place over here at the top of the light blue. And while it sits here at the top of the light blue, which is at this probe, does cursor number 2 show me 8 volts down here? Does the O-scope confirm our calculations with Ohm's law? It's pretty amazing. So we use the O-scope to confirm the peak values of the waveforms, and we use a digital multimeter to confirm the RMS values. Okay. So any questions about how to, let's go ahead and confirm this last one. I'll move the cursor number 2 to the tippy top of the blue waveform. And what's cursor number 2? 5.0435. Pretty close to 5. We're happy with that. And even without the cursors, my friends, I'm going to move the cursors completely off the screen. Do we have markers on the vertical axis? Does it say voltage? Does it say 2.5 volts here, 5 volts here, 7 volts here, 10 volts here? Does the axis marking confirm that green waveform is hovering right at the 10 volt line? Okay. Does it confirm that the dark blue curve is hovering peaking right at the 5 volt line? So without the cursors, we can still use the division markers to be able to tell us how much voltage these waveforms are displaying. But when you have something like that light blue waveform that's in between 7.5 and 10. It's kind of hard to approximate. We can use a cursor, grab either 1 or 2, doesn't matter. I'm going to grab this one, lay it right down on the tippy top of the light blue waveform, and hover right about there. And we expected 8 volts, and guess what? We measure 8 volts. Pretty cool. Now, how about period? How do you count period? Well, you count it this way. You count it as the amount of time between the beginning of the waveform to the end of the waveform. And do we have a time mark? Do we have, let's see if I come this way. Oh, we came quite a ways. It doesn't matter. Okay. Okay, now it's in the middle of the display. That's fine. Do we have a starting point right here for all the waveforms? They're all in phase with each other. They're just showing the values at measuring at different points of the circuit. Do we have a time mark here? What is the time mark here? It shows us the number of microseconds per division right here. Yes? On the bottom of the screen, it shows us 200 microseconds per division. And it shows us this while we are in the run mode. If I go to pause this, this will show where the waveform stopped over a period of time. I need to have this in the run mode, so I hit my little run triangle, and do we see 200 microseconds for each division? Now, could you count with me the number of divisions from the beginning all the way to the end of one cycle? So how many divisions do you count here? Andrew, how many divisions do you count? How many large squares do you see between the 0 over here to where the one cycle ends?
Ask me that one more time.
Okay. The number of horizontal squares between where the waveform begins on this side, following this line, to where the waveform, the cycle ends on this side.
I count 5.
I count 5 squares. Does everybody agree we have 5 divisions? And what do you do with those 5 divisions right now on your calculator? Multiply by 200 microseconds for each division. So do that now. Take your calculators, turn them on, clear, 5 times 200 micro, and hit equals. And what does your calculator display in terms of time for one cycle? The time for one cycle calculates to be what value? Question goes to Tony. Tony, huh?
Yeah, I'm here.
Yeah,
let me see, time is 1 millisecond.
1 millisecond. How many people agree with 1 millisecond gives us a thumbs up? While that number is on your calculator, that is the time for one cycle. There's a quick 2-button push to convert time into frequency. What do? You hit your reciprocal key,
1 kilo.
and then you hit equals. And what is the frequency that you calculate, Gregory?
1 kilohertz.
1 kilohertz. And does that confirm our source frequency at the very beginning? We said this would be 1 kilohertz, and we got 1 kilohertz by measuring right off the display screen, yes? This is a really, really powerful piece of software. This will be one of the assignments that you'll be doing, and other lab assignments similar to this using this piece of software. And as I've said, this piece of software is an online software, so it doesn't matter whether you're using a Mac or whether you're using a PC. Everybody will be able to use this software to be able to generate these wonderful waveforms and confirm these values. So we went through this exercise together. We went through the exercise of this circuit. We did a VIR analysis of this circuit. We filled in the VIR table for this particular circuit. We had predictions for voltages across each of these. We put in test points, and from each of these test points, we have an expectation how much voltage to ground, and we were able to display a waveform that confirms those voltages to ground. Is everybody okay with this demonstration? Would you like to see one more?
How do you get those cursors?
Oh,
I made that whole schematic for the circuit.
mhm.
My cursors are gone
Your cursors are gone. Well, you first of
after
all,
I split.
okay. So while this is running, you have a cursor control on the right-hand side, which you can flip. So the arrow points, you want it to point down to open up the cursors. And then you pull down here. What type of cursor do you want? You want the x-axis cursor? X-axis cursors go this way. If you want the y-axis cursors, which is what we were using, they go this way. If you have a track, we're using, this allows us to track points. We're not using that particular one just yet, but let's stay with the y-axis. So you have to open up the cursor control panel, select y-axis, and then you have your cursor 1 and you have your cursor 2. So cursor 1 and cursor 2. And so we can, once the cursors appear, then you grab them and you can place them anywhere you want. So if I place this guy here, cursor number 2, at the tippy bottom of the light blue waveform, we expect negative voltage. Does it show me in this window underneath cursor 2, I have a negative 8.0012 volts? Yeah, I expect the negative voltage and it reads out as a negative voltage. Okay. Are we good with this particular guy? So once you do this, hold on, don't get excited. We did a lot of work. What you ought to do is in the file navigation menu, which is this crisscross up here, select this. Oh, you got to stop the circuit from running. Okay, once the circuit is stopped, then you select this guy and you do a save as. So please do a save as. And when you do this as a save as, this, and you put in the title of the circuit, this will be capital AC, 3 capital R, because there's 3 resistors, and your name or initials. I'm a sample. Okay. So AC 3 resistors, I'm a sample. And then you click OK. And now it will become part of your library. Actually,
Professor, I have a question.
yes.
Does this do a triangle and square functions?
I haven't seen it do this yet. I haven't played with it enough to see whether it does. Again, this is a watered down version of MultiSim, which is what we use in the classroom. And MultiSim in the classroom does just about everything. But I'm so excited that this is able to do sine waves and gives us waveforms and gives us the ability to be able to read the waveforms and verify the predictions that we make on paper. So
this really is amazing. Thank you. Yeah.
Yeah. So, and it's free, and it's not platform specific. You can use this on a Mac as well as on a PC. So, so this is pretty good for free. Okay. Any other questions at this point?